Alright, here's our video on current electricity, the other type of electricity. Static electricity was the first one I went through. That involved our electrons on insulators, places they couldn't move around. Current electricity involves our electrons being on conductors. Again, electrons, the negatively charged subatomic particle found outside the nucleus of atoms. All electricity involves electrons in one way or another. Again, thus the name. Conductors, the new word in this particular video. Conductors are substances that electrons can flow through easily, and I've got several pictures of conductors up here. I've got some copper wire, the most common type of wiring used in homes. I've got some aluminum pipe here. The aluminum pipe can conduct electricity pretty well. Aluminum being nearly as good a conductor as copper. Gold chain. Gold is one of the best conductors out there. And a picture of a nail and some screws here. And again, made of metal just like the rest of them, so a good conductor. All the pictures I put up here are metals. Metals are by far and away the best conductors of electricity. The reason for that, their electrons and their outermost energy level are very loosely held onto. It's very easy to kick the electrons out of those outermost energy levels and make them move. So they make very good conductors. There are conductors outside of this. There are things that are not metals that will conduct electricity. Graphite, like in your pencils, will conduct electricity. And salt water. Salt water is an excellent conductor of electricity. That's why you would never want to go swimming at the beach in a thunderstorm. If lightning were to strike the water, it can flow through that water very easily. And again, it has to do with charges. In this case, with the salt water, it has to do with the positive and negative ions that are produced by the salts in that water. There are two types of current electricity, and that's really what this video is going to focus on, these and Ohm's law. There are two types of current electricity, alternating current and direct current. Alternating abbreviated AC, direct current abbreviated DC. Let's take a look at what each one of those are. Direct current is current that flows in one direction. In a direct current system, the electrons go one way and one way only, from one side of the battery to the other. In this illustration that I've put up here, it's kind of hard to see. Let me see if I can turn the lamp up a little bit brighter, make it easier to see. In this illustration, we have a very simple circuit. We have a battery here, a lantern battery, attached to a switch and a light bulb. What happens here is the electrons will flow out of one of the battery's terminals, through the wiring, through the switch, through the bulb, and back to the battery again. And they will flow in that direction. They will flow in that one particular way all the time. They will never turn around and go backwards. They will go from one side of the battery to the other in one direction all the time. Direct current, what I always tell my students, the direct means is the electrons will flow directly from one terminal on the battery to the other. Batteries are the most common source of direct current. Solar cells, solar panels will also produce direct current. You'll see those from time to time. Most of our objects, most of our electronic devices will use batteries to produce their direct current. In an alternating current system, the electrons will switch directions, will change directions. They'll flow one direction, then they'll turn around and flow back the other. Anything plugged into an electrical outlet is using alternating current from that outlet. What happens in this little light here is the electrons will flow out of one side of the outlet through the bulb, then they turn around and they flow back again. Flow one direction, then they turn around and flow back. Flow one direction, turn around and flow back. Back and forth, alternating direction. That's the name, alternating current. I am going to put a video up here that involves some of the simulators on the University of Colorado's websites. If you want to get a better understanding of alternating current, direct current, and what's happening with the electrons, make sure you check that video out. Some of the things you have to know about direct current and alternating current, some of the pros and cons about them. Direct current, what's good about it, it's a safer form of electricity. When you're shocked with direct current, it is less lethal. Not to say that it can't kill you, it certainly can. But it is less lethal than alternating current. The reason for that, because direct current doesn't change direction, it's never turned on and off. It's always on or it's always off. There's no back and forth. As a result, when you're shocked with direct current, it contracts your muscles one time, keeps them contracted until the electricity is shut off. That is better for your muscles, that is safer for your heart. It's also more useful. Most of our electronic devices use direct current. Problem with it, the drawback, it can't travel very far. You cannot transmit direct current very far down electrical wires. So getting it to your house would be a very costly, very difficult thing to do. Alternating current does travel greater distances. It can travel for hundreds of miles down electrical wires. As a result, it's much cheaper to produce. Far fewer power plants are needed to produce an alternating current system. Big drawback with it, it is more dangerous. Every time the alternating current switches directions, it is off for a millisecond. So literally, in an alternating current system, the electricity is turning on and off, on and off, on and off, so fast that you can't see it, you don't notice it. When you have a lamp plugged into an alternating current system, you don't see the lamp flashing on and off. It happens too fast for us to perceive, but it does happen. If you've ever been shocked with alternating current, it feels like a buzzing sensation. The reason it feels like that buzzing sensation is because the current is being turned on and off. Your muscles are contracting, relaxing, over and over and over again, and that is that buzz, that is that vibration that you feel. In our electrical outlets in the United States, it turns on and off 120 times every second. Now imagine if that were to get to your heart muscle, making your heart muscle literally beat 120 times a second, tears it apart. And that is really what makes it so dangerous. The other thing that I need to talk about as far as current electricity goes is Ohm's law. We talked a little bit about voltage and current in our electricity unit. Voltage is the potential energy in electrical systems. It's the push that moves the electrons around. Current, represented by I in this equation, is the kinetic energy in our electrical systems. It's the actual energy the electrons have as they move. What Ohm's law tells us is the relationship between voltage, current, and a new one here, resistance. Again, voltage is the potential energy in your electrical system. Current is your kinetic energy in your electrical system, the movement of the electrons. Resistance is like friction in an electrical system. It tells us how easy or hard a time the electrons have moving through the circuit. If resistance is low, they have a real easy time moving through. If resistance is high, they have a very difficult time moving through. Resistance acts a lot like friction. If there's a lot of friction in a system, objects have a hard time moving. If there's little friction, they have an easy time moving. Friction will turn mechanical energy into heat. Resistance will turn electrical energy into heat. So very similar to friction. And what Ohm's law tells us is how all these variables are related to each other. I'm not going to look at the math on here. The math is very similar to all the things we've done before. I do, however, want to look at those relationships. Two in particular you have to know, the relationship between voltage and current first. Voltage and current are directly proportional. That means they change in the same way. When one goes up, the other goes up. When one goes down, the other goes down. And it's pretty common sense. The more voltage I have, the more potential energy I have, the more kinetic energy I'll have. The more current I can produce. The less voltage I have, the less current I can produce. Kind of like a ball on a hill. Low voltage is like a real small hill. If you have a real small hill, the ball's not going to roll very well. That low potential energy will give you low kinetic energy. If the voltage is low, you'll have low current. High voltage is like a tall, steep hill. If the hill is tall and steep, the ball has a lot of potential energy. It'll roll much faster. High voltage gives you high current. Very similar concept to mechanical energy. Works very much the same way mechanical energy works. The other relationship, resistance and current. You have to know how those two are related. They are inversely related. Inversely means they change in the opposite way. When one goes up, the other goes down. Increasing resistance will decrease current. And again, if we remember that this is a lot like friction in mechanical systems, again, it makes sense. If you have a lot of friction, you'll have less motion. If we have a lot of resistance, we'll have less current. And vice versa. If we have very little friction, we have a lot of motion. If we have very little resistance, we'll have a lot of current. Again, very similar to the concepts in mechanical energy and big moving objects. The only difference is we're dealing with something much smaller here. We're dealing with electrons moving around. But if you can make those relationships, you'll understand it a whole lot better. If you have issues with the math, make sure that you ask me during class or post some questions on the wall. And make sure you understand these relationships because they're just as important as the math.